Hi friends, welcome back to Acharya Gurukulam. Today's topic is Assessment of Liquefaction Potential, a discussion as per IS 1893-2023 draft code. In this video, I am going to explain the introduction, estimation of cyclic stress ratio, estimation of cyclic resistance ratio, liquefaction potential, and a graphical representation of cyclic resistance ratio. Liquefaction occurs when saturated, loose, sandy, or silty soil is subjected to strong ground shaking from an earthquake. The shaking causes the soil particles to lose contact with each other and become suspended in the pore water, effectively turning the soil into a quicksand-like state. A photograph shows the liquefaction phenomenon during 2011 Christchurch earthquake. Now we'll discuss the estimation of cyclic stress ratio. The local surface produces horizontal motion at maximum acceleration as Amax under earthquake load. The weight of the column is gamma into Z, that is gamma is the soil bulk density and Z is the depth of the soil column from surface. As we know that F is equal to MA, so M is represented as W by G into A and W is represented gamma into Z divided by G into A. Now we'll replace this gamma into Z as sigma into V sigma into V naught. F is equal to horizontal seismic load on a soil column in the unit width and length in kilonewtons, and M is the total mass of the soil column. W is the total weight of the soil column. Amax is the ground level maximum acceleration or the maximum acceleration at the ground level. And sigma V naught is overburden stress at the bottom of the soil column, which is represented in kilopascals. Considering the soil column with the unit length and width, therefore F is equal to tau max. Tau max is equal to A max by G into sigma V naught. On both sides, we divide with effective stress, that is sigma V naught prime. Then the equation becomes tau max divided by sigma V naught prime is equal to sigma V naught divided by sigma V naught prime multiply with A max by G. And this RD represents the reduction factor, stress reduction factor. Why we multiply with stress reduction factor is due to the earthquake load, soil column is not rigid. In fact, it is deformable. So the equation shall be multiplied by stress reduction factor related to the depth. So that's why we multiply with the stress reduction factor RD. The stress reduction factor RD decreases in nonlinear loss with the increase of the depth. The National Earthquake Committee, that is NCEE, suggests that RD can be obtained by the following equation from the perspective of practical engineering, where RD is equal to 1 minus 0.00765 into Z, where Z value is in between 0 to 9.15 meter. And if the Z value is beyond 1.95 meter, up to 23 meter, then we use RD is equal to 1.174 minus 0.0267 into Z. Because the change of the time history of the shear stress in soil shows irregular shape when earthquake occurs, it will be replaced by the average equivalent shear stress in specific application of tau cyclic is equal to 0.65 into tau max. This 0.65 is equal to 1 divided by 1.5. Then the cyclic stress ratio is equal to 0.65 into RD multiply with sigma V naught divided by sigma V naught prime multiply with A max by G. If the value of PGA is not available, in the earlier case, the A max value is where the maximum acceleration is available for a site. If the value of PGA is not available, then the ratio of A max by G may be taken as equivalent to earthquake zone factor Z. A tabular column is provided as per IS 1893-2023 draft code for various earthquake zones. The Z factor values are given here. Then we'll discuss about the estimation of cyclic resistance ratio. The cyclic resistance ratio is correlated to core penetration test and standard penetration test, penetration resistance after application of overburden stress corrections. SPTs, the various procedural corrections for arriving at a standard energy corrected N60 value are summarized in address and Bollinger in 2008 and 2010. For CPTs, a procedural aspect which warrants a clarification for liquefaction applications in correction of a measured tip resistance, that is QC, for unequal end area effects, which is given by Campanella et al. In 1982. The soil's CRR is dependent on the duration of shaking, which is expressed through an earthquake magnitude scaling factor, that is MSF, and effective overburden stress expressed in K sigma factor. The correlation for CRR is therefore developed by adjusting the case history CSR values to a reference M is equal to 7.5 and sigma V naught prime is at 1 atmosphere. The capacity of the soil shall be estimated through the cyclic resistance ratio, that is CRR, for an earthquake of magnitude loading using an expression CRR is equal to CRR MW at 7.5 magnitude and sigma V naught prime at 1 atmosphere multiply with MSF, that is a modified scaling factor, and K sigma, where K sigma is the effective overburden stress. CRR reflects of the liquefaction resistance of the soil under a seismic load. It could be evaluated by dynamic triaxial test, SPT, CPT, shear wave velocity test, and other in-situ tests. But undisturbed sample is relatively difficult and expensive in sandy soils. In-situ test become the commonly used evaluation method in engineering area. SPT and CPT have been widely applied in engineering applications. Now here we'll discuss the CRR equations for various cases for clean sands, for clean sand and sand with non-plastic fines. This is categorized further into 4 categories. One is from cone penetration test, second from standard penetration test, third from dilatometer test, fourth from shear wave velocity test. So these cases are given as per IS 1893-2023 draft code. From cone penetration test, the equation is given, a lengthy equation, where QC1 NCS is equal to QC1N plus delta QC1N. The equations are given here. Delta QC1 is equal to 11.9 minus QC1N divided by 14.6 into exponential of the term. Here for calculating delta QC1N, you need fine FC. What is FC? FC is the fineness content or percentage of fines. Second, from standard penetration test, the equation is given similar to the first case. A lengthy equation is given here, where N160 CS is equal to N160 plus delta N160, where delta N160 is equal to exponential of the term where FC is involved. FC is percentage of fines. The equivalent clean sand adjustment delta QC1 and delta N160 are empirically derived from the liquefaction case history data and accounts the effects of percentage of fines. That is the fineness content. The adjustment for SPT based correlation is unchanged from that used by the Edis and Bollinger in 2008, but the adjustment for the CPT based correlation has changed. The changes in the equivalent clean sand adjustments for the CPT are attributed to the changes in the updated case history database. N160 is greater than 30, then the sandy soils is considered unliquefiable. Then third case is from dilatometer test. Correlations for predicting liquefaction resistance based on the DMT KD value has been proposed by 3 investigators. Those are Monaco et al. In 2005, Sai in 2009, and Robertson in 2012. The equation is given where CRR is the equation is given. CRR is equal to 93 into 0.025 KD whole square plus 0.08. The above equation is defined for ID greater than 1.2, and the KD is in between 2 and 6, where ID is the material index. The horizontal stress index is denoted by KD, which is given by KD is equal to QTNCS divided by 25, where QTCS TNCS is approximately equal to QC1NCS divided by 25. You at in 2004 would suggest that KD is equal to 4 in a very loose sand case. Next, third case from shear wave velocity. CRR given by Andres and Stroke in 1999 for MW is equal to 7.5 earthquake, which is defined as CRR is equal to 0.022 multiply with VCS1 divided by hundreds whole square plus 2.8 into 1 divided by VS1 star minus VS1 minus 1 by VS1 star. Following the traditional procedure for correcting SPT, blow count and CPT tip resistance to account for overburden stress, where overburden stress corrected shear wave velocity Vs1 for clean sand soils shall be estimated as Vs1 is equal to Pa divided by sigma V prime whole to the power of 0.25 into Vs. Vs1 is overburden stress corrected shear wave velocity. Pa is reference stress of 100 kPa or about atmospheric pressure, and sigma V prime is initial effective overburden stress, which is represented in kilopascals. And Vs1 star can be assumed to vary linearly from 200 meter per second for soils with fine content of 35% to 215 meter per second for soils with fine contents of 5% or less. Next, the magnitude scaling factor shall be estimated using the expression MSF is equal to 1 plus MSF max minus 1 into 8.64 into e to the power of minus 0.25 m minus 1.325, where MSF is equal to 1.09 into QC1 NCS divided by 180 less than or equal to 2.2 from CPT, and 1.09 into N160 CS divided by 180 less than or equal to 2.2 from SPT. The overburden stress correction factor K sigma shall be estimated using the expressions. K sigma is equal to 1 minus C sigma natural logarithm of sigma V prime divided by PA less than or equal to 1.1, where C sigma is equal to 1 divided by 37.3 minus 8.27 into QC1 NCS whole to the power of 0.264 less than or equal to 0.3 from CPT. And for SPT, the value of C sigma is equal to 1 divided by 18.9 minus 2.55 under root of N160 CS. Next is the liquefaction potential. The assessment of liquefaction potential of a site is given by Fs liquefaction is equal to CRR divided by CSR. The liquefaction potential, that is Fs is less than or equal to 1.2. It is unsafe against liquefaction, and Fs is in between 1.2 to 1.4. The ground settlement results from the earthquake loading shall be verified, and if Fs value is greater than 1.4, it is safe against liquefaction. Alternatively, a graphical representation is also given in IS 1893-2023 draft code. A graph is drawn between CSR. A graph is drawn between CSR and CRR versus QCN1. If you know QCN1, then we can find out the CRR value for various percentage of fines without much doing the calculations. This is the graph for a revised deterministic CPT based triggered correlation. And there is another graph drawn between CRR and N160 for various percentage of fines, 5%, 15%, and 35%. And another graph is drawn between CRR and KD values uh, for various researchers. This graph is represented by Monaco et al. In 2005, and this graph is represented by Sai et al. In 2009. And the graph which is drawn in between is Robertson in 2012.